So we'll work through one more example, and this is the second part of investigation one, where you see, this is page 380, right? So this is another experiment, and this time the two variables is the temperature, and the other one is the area of the petri dish. And this is the formula that gives us our Spearman's rank correlation coefficient. I can add coefficient here. Coefficient. And it looks very complicated, but the procedure is really summed up on page 380. You shouldn't follow that because it's wrong, but we'll just make a little change to it. So the first thing you do is to find the sum of the squared differences between the ranks. So once you have a number here, you can multiply that number with 6 and then divide it with this expression here. Now the n here is the number of numbers that you have here. So the number of differences squared. And you can sort of fill out this formula and divide it by that number. And finally, you subtract everything from 1 to get your R value. So again, this looks like a P, but this is really a Greek R. So for our second example, it's going to look a little different. So we have these data here, and we can also represent that in a diagram. So we'll put in a scatter graph like this. Now, the way this diagram is different is it looks more or less like a linear correlation, but you have an outlier down here. And what we'll find is that the Spearman rank correlation coefficient is not as much affected by outliers than Pearson's. So it's less affected, so you don't really have to make the same adjustments and remove outliers the way you might have to with Pearson. So we'll find Pearson's correlation coefficient first. Same as before, you can write equal sign, correlation. Again, if you're working with the English version, just type this in English instead and use a comma rather than semicolon. Okay, so relatively strong negative correlation. But the reason why it's not super strong is because of the outlier. Okay, so now we'll set up the ranks. So how do these numbers rank in relation to each other? Going from 1 is the highest, and let's see how many? 8. 8 is the lowest number. Okay. And again, the reference area is all these numbers. And we want a descending order. Now, again, we have to adjust, up here so that we don't change the reference area. So this is what the formula should look like. And we can copy that to the next cell and just make a change to B. All right, so we'll copy these down like this. And now we have the rank for each data set. The difference is going to be one of them minus the other. And it doesn't really matter which way you write this. You don't have to take the biggest number first. The reason for that is you'll see that some of the numbers are negative. It doesn't matter because once you square them, they're going to be positive anyway. So this is why the difference is squared. So, okay, we take the number and then multiply it with itself. And now we'll just copy that all the way down. At the bottom here, we're going to sum up all the squared differences. So this is the top part of the formula here. This sigma sign is the sum of squared differences. Like this. And again, if you want this in English, you just write sum instead of summer. So once you have this sum, you can multiply that with 6, just like in the formula. So this cell multiplied with 6. See, more space here. Okay, so then we're going to divide that number. Divide that number with n, which I'm going to write down here. So divide that number with this cell multiplied with this cell multiplied with itself minus 1 and then brackets. Now, if you don't have a number down here, it's going to be a mistake here. But the n is the number of numbers. That was count, wasn't it, in English? So we're going to count. Oops. We're going to count the number of numbers in this reference area here. 1, 2, 3, 4, 5, 6, 7, 8. So it should be 8. Yeah. Then you subtract this number from 1. 1 minus this. Oops. Yeah. Equal sign. 1 minus this equals 0.976 negative. So now we see that we have a much stronger, stronger, you have a very strong correlation even with the outliers. So we can see that the Spearman's rank correlation coefficient is not as affected by outliers. In this case, we did have a linear correlation, but it was badly affected by the one outlier that we had. So another example of how you find it. And now your next assignment will be to do the same thing for question 5 on page 386. So spreadsheet and solve in the same way. In the exam, you would have to do this by hand, but we don't have to do this while we practice. And it's this will hopefully give you a better understanding of what you're doing. So this will be the next assignment for Thursday, probably. Yeah. So I'll let you know in OneNote as well.